All right, so there's our explicit formulas that are on our reference sheet again, okay, with all of the variables defined in case you forgot what they are. And in number 3, it says write an explicit formula called a sub n for each of the following sequences. So in part A, we have to figure out, are we going to use the first formula, which is arithmetic, or the second one, which is geometric? And we won't be able to tell until we figure out, are we adding or are we subtracting? And so in this one, to get from 9 to 12, and 12 to 15, and 15 to 18, I think you're going to realize that you have to add 3 each time to move you from term to term. And so because we are adding, this is going to be arithmetic. So we'll go ahead and say a sub n equals, a sub 1 equals, n equals, and d equals. Our d is what we just figured out, is our difference of 3. Our first term was 9. And since we are writing a formula called a sub n, anything with n in it is going to stay a sub n, or stay n. Okay? And so we'll end up with a sub n equals, our first term is 9, keep the plus sign, in parentheses, the n will stay n, minus 1, close it up, and then our d, or our difference, is 3. And that's an okay formula. It's just not cleaned up to its simplest form. And so if we want that to clean up to our simplest form, we're going to go ahead and distribute. However, you got to remember you're distributing this way. And you're going to get 3n minus 3. And that's an okay formula too, still not cleaned up to its best. And so I'll put the 3n first, and then the 9 minus 3 will make a positive 6. And that would be a better formula. And now we could go ahead and find any term we want. So if we wanted to know the 100th term, we'd plug in 100 for n, and we'd be able to know what the term was, okay, without writing them all out. Okay. Next one up, we got to figure out how are we getting from 5 to 10, and 10 to 20, and 20 to 40, and hopefully you're realizing you have to multiply by 2 all the way to do that. And since it's multiplying, it's geometric. Okay? And in our geometric sequence, we could write the variables out again, but I think some of us are getting the hang of it, that a sub n would stay because it has an n in it, and I'm writing a formula for n. Okay? My first term would be replaced with a 5. In parentheses is r, which is your ratio, which is what you're multiplying by, which is 2. And then again, the n would stay n because we're writing a formula for a sub n. Okay, so anything with n in it stays. And that's it. You can't clean this one up. A lot of people will try to multiply the 5 and the 2, but remember you can't do that because the exponent of n minus 1 is only on the 2. And if you multiply 5 and 2, then the n minus 1 would be on both the 5 and the 2. Okay, and we don't want it to. All right, and then there's our formula. Okay? In our third one here, we need to figure out how we're getting from 3 to 1, and 1 to 1/3, and 1/3 to 1/9. And hopefully you are realizing that you have to multiply by a third. Okay? All the way through. And since we're multiplying by a third, then this becomes geometric. And our geometric sequence will be a sub n equals our first term, which is 3, our ratio of 1/3, which is what we're multiplying by, and then this will stay n minus 1. And again, that cannot be cleaned up. Okay, so we're going to keep it. In our last sequence here, we got to figure out how we are getting from 3 to -2, and -2 to -7, and -7 to -12, and hopefully you are realizing that you are adding a -5 all the way through. And so because you're adding, then this becomes arithmetic, and our formula would be a sub n equals our first term, which is 3, plus, in parentheses, that would stay n minus 1, and then our d is a -5. Okay, and that's an okay formula. Like I said, it's not in simplest form. I always like to clean them up in simplest, so we'll say 3 plus. Doesn't take long. It's just a little distributing and a little combining of like terms, so nothing hard. So that's going to be a -5n, and then that's going to be a +5. Okay. One more cleanup. We're going to take the -5n and put it first, and then we'll combine the numbers in the front and at the back. 3 plus 5 is a +8, and there is our formula. So we can find any term in the sequence that we wanted to. Okay. All right. So now in number 4, it's giving us a sequence. Same thing that we've been doing, and it wants us to algebraically determine a sub 75, which is the 75th term. Okay. So let's go ahead and do the same thing we were doing up above. Let's determine what the sequence is. So we got to figure out how to get from -9 to -5 to -1 to 3, and I believe we are adding 4, right? And since we're adding, this becomes arithmetic. Arithmetic would be the first formula called a sub n equals my first term, which is -9, plus n minus 1 times my difference of 4. And we could, again, leave it like that if we wanted to, or we could go ahead and clean it up like we were doing up there. This is going to become a positive 4n minus 4. We'll put the 4n first. -9 minus 4 is -13, and there is a nice cleaned up formula, okay? Not our answer, because they want us to now use the formula to go ahead and find a sub 75. So we'll say a sub 75 equals 4 times 75 minus 13. And our 75th term is going to come out to be 287. And there's our 75th term. Okay, all right, let's take a look at number 5. The diagram shows the number of blocks in each figure. It represents the first 3 terms of the sequence. Assume this pattern continues. Write an explicit formula that determines the number of boxes in the nth figure. So the only difference here is that they're not giving you the sequence with numbers, they're giving you a sequence with blocks. So if we go ahead and count how many blocks are in each one, then we'll have our sequence. So in the first one, there are 5 blocks. In the second one, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. And in the third one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, and so now that we have our sequence, now we'll figure out that we are adding 4 to get from term to term to term, right? And since we're adding, that becomes arithmetic, and therefore arithmetic, we'll go ahead and write our formula would be a sub n equals our first term, which is 5, plus n minus 1 times our difference of 4. If we go ahead and clean that up, that would become a 4n minus 4, and a cleaned up formula for this pattern of blocks would be 4n. 5 minus 4 is a positive 1, and there's our sequence, or our formula for our sequence, okay? Part B says algebraically determine what figure will have 49 boxes. So now we don't know what term will have 49 boxes, therefore we have to realize that 49 is our output. And since it's our output, we're going to go ahead and put 49 in the output spot, which is in for a sub n. We'll keep the 4n plus 1 here. We'll go ahead and subtract 1. That's going to give us 48 equal to 4n. And we'll divide by 4, and n will come out to be 12. So it will be the 12th figure should and would have 49 boxes in it. Okay. All right, one last one. Number 6. It says that the number of squares in the diagrams below represent the first 3 terms in a sequence. Algebraically determine what figure will have 4,374 squares. Whew, that's a lot of squares. So I already have a thought that this might be geometric, but let's go ahead and see. All right, so the first figure has 2. The second figure has 4, 5, 6. Third figure has, let's see, what is that? 1, 2, 3, 4, 5, 6. 6 and 6 is 12, 13, 14, 15, 16, 17, 18. All right, and to get from 2 to 6 and 6 to 18, we're going to realize that we are multiplying by 3. And so I was right. Because we're multiplying, this is geometric, and our geometric formula says a sub n equals our first term, which is 2, in parentheses what we're multiplying by, which is our ratio of 3 raised to the n minus 1. And remember, those formulas cannot be cleaned up. As much as you want to multiply 2 and 3, you cannot, okay? It'll change your formula. And so now we want to know what figure will have this many squares. We have to realize that this is our output. And so we're going to go ahead and put that number in the output spot. And we'll be able to go ahead and figure out our end value, which will be what term or which figure will have that many. And again, we're solving for an exponent. This is a log question, except we're not ready for logs until we get rid of this 2. And so when we divide by 2, we end up with 2,187 equal to 3 raised to the n minus 1. All right, so now we're ready for log. So we'll write log. The base is 3. The number is 2,187, and it's equal to our exponent of n minus 1. We'll change this into a division problem so we can put it in our calculator. It'll be log of 2,187 divided by the log of 3, and that'll equal n minus 1. Okay? Put it in our calculator, and out pops 7 equal to n minus 1. We'll go ahead and add 1, and we'll end up with n equals 8. So it will be the 8th figure, if it was drawn on our paper, would have that many boxes in it. Good thing that I didn't draw the 8th figure. That'd be a lot of counting. Okay. All right, guys. Very good. I will see you guys on the next day of notes.